Hello and Assalamu alaikum everyone. I am Osama Aslam. So today we will see how we can write a subroutine, any subroutine for Abaqus, like ultra C load, D load, V load, or any subroutine. So for that, actually, first of all, we must know our equations, like what is our criteria to write for that subroutine. And secondly, we should go to the official Abaqus website for the subroutine. We should take that structure and then just like update our that uh, code. For example, uh, I want to write ultra C load subroutine. That is, if we are not applying force as a pressure, so then if we are applying as a traction force, then we can use this ultra C load. For example, also deload subroutine. The main thing we should refer to the Abaqus official like code. See, they have provided the basic structure, so we should follow that. And then here in the middle part, we just update our code. So VLOAD, DLOAD, anything we can first of all refer to that. Yes, so you see here. And then, okay, we try this one, ultra load. So we will copy this and paste here. So let me tell you like what is the structure subroutine. This is comment, take another comment. You can also write with the exclamation mark. This is stu- uh, the system will not read this. Then this is to include library. For this one, this is alpha is the load, T user is the direction, K step is the step number, increment number, time, number of element, number of points, coordinates, direction of angle. Then this is load type and this is S name. Like we will see here, this is a basically this is a total library. This is a dimension time 3, T user load direction 3, XYZ, time, coordinates, 3, direction, and also the angle. Then this is we have to say. Then you can just remove this. And then today I will show you like I am applying a tornado load on that is a moving load actually. So what is its scenario? And on a turbine. So this is a turbine, X and Y direction. So this is a tornado. It has actually it has three components, like radial velocity, tangential velocity, and vertical velocity. But because this is a pole turbine structure, vertical member, so we can ignore vertical velocity that is very low. So currently the tornado is at minus 500 direction and then it will move toward the turbine with some increment, time increment in the X direction. Then it will pass the turbine and then finally it will reach 500. So this is the scenario. So we can calculate R by this formula like simple trigonometric function. So anyone you can use. I'm using this Cohen model. So for this is a boundary layer formulation. This is radial velocity, tangential velocity, vertical velocity within boundary layer. And then if it is, and then this is outside boundary. This is within boundary layer. So this is the formulation. So we have the structure for subroutine. Also that we know what we want to do, and thirdly we know the equations. So what we will do like here. First of all, we need to define the variables and parameter. Mean real. In this Fortran code. We define that is changing with time or something that we define real, and then that the some value or constant that is a parameter. So judge from the what you can do, you can also make an Excel sheet where you know that okay, R is changing, RC naught is a constant. Here you must see that okay, I need RC naught, delta infinity, Vmax. You must see from formulation what are the constant and what are the variables you must have. I must have B, this is a constant value. or you can say if it is changing, if it's we're taking as this one, then eta. So these are the, so from your question you know that okay, these are the things I must have. So okay, height, radius, and then you calculate boundary layer by formulation BV. Okay, so you know that. Then what you will do that, okay, so I have already done, I will not write, I will make the video so long. So here, okay, you already defined parameters. Real are this Vmax, I already told you. You must know your variable. And then parameters that are fixed. You can take any value according to your Vmax 90 meter per second, 100 meter, delta infinity, 1000 meter pi value, it's fixed. And then, okay, you can define the tornado motion parameter. You can also take the help for the chat GPT and it if it is possible. So this is the at this speed the tornado is moving. So then you can, this is the initial coordinate. I told you like here I'm taking minus 200, you can take 500 according to the, and then this is how like moving x initial coordinate plus vx v into time, like it is moving with some time. Okay, and then this is the formula for r, same thing, this one, x naught minus dv plus y square. So you must know your formulation first of all. Then to calculate theta, this is like if, so now what is that? Now this is a one parameter like delta. I told you this is the formulation delta 1 minus x. So this is the same thing. We'll read 1 minus exponential zero point 0.5 r over RC naught. Then tangential velocity formula. And then radial velocity formula. And then this is how we apply in the, because I told you we are taking two parameters like two velocities, radial and tangential, so we can ignore vertical velocity. So this is T user is like in the VIX is applying in the X Y Z X direction, and VYZ is applying in the Z direction. So Y is vertical, so we are ignoring that. Okay, so the subroutine is complete. Now let's see in uh, Abaqus how we can apply that. Okay, so this is a model turbine pole. We will see that. Okay, so see this is uh, yeah. So this is X direction and this is Z direction. Right. So why we are ignoring? So now what we will do, like okay, create a new job and go to general. We already saved that file. Okay, this is the file for subroutine. You can do you can use multiple process. 40. Yeah, it's 40 here. Okay. Okay, so you can submit it. So you will see that it started running. So, see, it started running. So it will take some time. So I can show you the model with that time. So this is a dynamic analysis, obviously, because tornado is moving. So the step time is 0.5 minimum. Total time 20 seconds. 0.2 initially 0.5 and yeah, minimum 0.002, and you can do this, and we will see that if it is already running or not. Yeah, it will take some time because okay, so when the analysis will complete, I will tell you. So now you have seen that the analysis is complete. As I told you, the step was smooth, 0.5. So the total was 20 seconds. So this it is dynamic analysis. So let's see the results actually. Okay, so you will see that. Okay, let's play here. You will see. Okay, so this is the analysis, and you can see that the wind passes by the turbine, tornado is passing. Okay, so first of all, what happened? Okay, you will see that. Let me show you. See this. So first of all, the tornado comes here, it passes, and then it moves away. So you can see its effect on the turbine. So yeah, this is so the it means that the subroutine is written correctly and it's working. So you can write any subroutine. I told you what are the steps. So I will upload this subroutine via Google Drive. You can ask for the access and ask any questions. Thank you.